Okay, so good morning. My name is Alexandros Stamatakis. I'm a researcher myself in the field of computer science and bioinformatics at the Heidelberg Institute of Theoretical Studies and at the Karlsruhe Institute for Technology. However, today I will do something new, so I'm kind of rather nervous. I will try to take on the role of a science journalist and interview Professor Warner Marzocchi, who is currently a professor of geophysics and of natural hazard forecasting at the University of Naples, Federico II, and at the Scuola Superiore Meridionale. So his main research focus is on seismic and volcanic hazard analysis, earthquake and eruption forecasting, and statistical seismology. And so this is where our connection, that we both do statistics in very different scientific domains. So to quickly introduce him, Warner received his first degree in earth sciences back in 1987 and his PhD degree in physics from the University of Bologna in 1992. So among numerous other activities, he has been visiting professor at the Institute of Statistical Mathematics in Tokyo, Japan, and a visiting scientist at the University of Southern California. He's also active in a lot of committees. So I've just picked two that sounded pretty cool. So he's a member of the Southern California Earthquake Center Advisory Council and also a member of the International Commission on Earthquake Forecasting. And the key goal of this interview is to better inform the broad public and also mainly the Greek public about current trends in earthquake forecasting, and to also discuss the recent seismic activity that we had here on the island of Crete. So, Warner, thank you so much for your time and for joining us for this interview. So, shall we get started with the questions?
Yeah, absolutely.
Okay. So the first or most basic question is, why did you actually study earth sciences, and what made you to study earth sciences?
Well, yeah, because it's a very tough question in the sense that probably what I like more in earth science is that we do not have the control of everything. I think that human beings tend to think they have the control. Actually, it's not. And earthquake and volcanoes in particular simply taught us this, that we do not have the control. We can learn something about them. We can try to live with them, but we do not have the control. Probably this is the most, the feature that attracts me most.
So was this somehow connected with your childhood in Italy, where earthquakes and volcano eruptions are something that you kind of experience from a little kid? As a little kid?
Actually, Italy is an earthquake and volcano country. And so every time that I visited a volcano, I was simply astonished. It's a very strange situation because you love what you see, and on the other hand, you understand that this could be a big trouble for people living nearby. So it's a very conflicting emotion that you feel every time that you see a volcano in particular.
I can understand that. So, like after studying earth sciences, then you did like a PhD in physics. So why did you switch fields?
Well, actually, I switched because at that time we didn't have a PhD in geophysics, but I felt strongly the need to become more quantitative and to have a much stronger background in mathematics and in physics with respect to what usually earth scientists have. And this is the main motivation that brought me to apply for a PhD course in physics. And it was very, very helpful for me because I feel the gap that I have in quantitative, in mathematics, for instance, in informatics as well, and also in general in physics. And that was very, very exciting to me. Having both background from earth scientist and from physics, it helped me a lot to understand what is the path that I wanted to take at that time.
And so was it like totally clear to you at the beginning of your PhD that you really wanted to investigate earthquakes and volcanoes? So was that like the overall goal?
At the time, I was interested in more general in earth sciences. Of course, I studied more earthquakes, but I also studied some complex behavior of the geomagnetic field at the time. For instance, the inversion of the geomagnetic field that happened in the past. And actually, what I thought it was very exciting in taking the PhD in physics was to see the problem in a different view. At that time, there was the first attempt to work on pattern recognition on the first neural network system. So to see a complex process like earthquake occurrence, like volcanic eruption occurrence, just trying to tackle the problem from a different perspective with respect to what has been used at that time. And for this reason, I strongly appreciate also to study the chaotic system, the dynamical system, just to understand a little bit more what is the process that stands behind eruption occurrences and earthquake occurrences.
So just to make it more clear for the general public, right, like neural networks and pattern recognition, those are methods that are currently known as machine learning methods or artificial intelligence methods that essentially help us to model or understand any sort of phenomena that we cannot really, that we don't understand enough to put them into an explicit model in a certain way. So now let's get a little bit to the, the recent earthquakes here in Crete that the citizens perceived as being rather unusual, and also there was like a large discussion in the media and the social media as well. So maybe we could go first to this magnitude 6 earthquake in Arkalahori, which is just like happened on the island of Crete and was very shallow. And so here, what at least according to what I read on Wikipedia, was unusual was this very kind of atypical activity before the major earthquake that hit the island. So for like a period of 6 months, we had this permanent earthquake, like many foreshocks, permanent earthquake activity in the area of Arkalahori. And typically, like, as a naive, interested scientist from another domain, you would think that this is something like an earthquake swarm that doesn't really have this one kind of main shock. But then it still gave like the this big main shock, despite this very high activity before the main shock. So is this something that is rare? Is this something that happened for the first time? Is this something that would have surprised you?
No, it didn't surprise me. Actually, earthquake occurrence is much more, there is a lot of different kind of patterns that you see before main shock. Sometimes the main shock come out from the blue sky and you just simply got a main shock. Otherwise, in other cases, you have a main shock that happen at the end of very long seismic sequences. And so this happened. It's not rare at all. And sometimes also you have a main shock that is comparable, and the aftershock behavior is completely different. We know that. We're able to model in some way this. And so we should avoid to think about that earthquake behave more linearly than what we are used to think. Usually most of the people say, okay, I got a main shock and then I have a power law decay. I have a decay in time of the number of aftershocks. This is on average, but we know that from sequence to sequence, you might have completely different behavior. We are able to track them. So, and in particular, coming back to the earthquake in Crete, I was not surprised that, again, sometimes it happens that you have a very long seismic sequences without any big earthquake. So the people tend to say that this is a swarm, but actually it's not a swarm, because after a big earthquake occurred, the swarm became a foreshock behavior. So personally, I don't like too much the distinction between swarm, foreshock, main shock, aftershock, because most of them can be decided after, not on the fly. And because if you see on the fly, this is a swarm, you are saying that is almost impossible to have a large earthquake inside the swarm. But this is not what you can say. And again, for instance, in the central Italy sequence, very recent sequence, we have a magnitude 6, just that occur without any particular seismic activity. People think, okay, this is a main shock. But after a couple of months, we got a much larger earthquake, North earthquake, 6.5. And so, well, no, this is the main shock. So the first one was the foreshock. So again, to me, it's very complicated to explain to the people. And an earthquake is an earthquake. And what we know is that every time that we have a sequence, the probability to have large earthquake increased. This is what we can tell you. And we can also calculate this probability. Usually that probability remains small. It means that most of the time you don't see a large earthquake. But on the other hand, this probability could be 100, even 1,000th of time larger than usual, than with respect to a period of time in which you don't see any earthquake. So in Crete in particular, I think that probably we are talking about 100 of times, but this is just an educated guess. I didn't make any specific calculation, but I would not surprise that that sequence increased the probability to have a large earthquake. So, but the most important point is that there is nothing unusual in what we have seen in Crete right now.
Yeah, so which brings us back to this original observation of yours that earthquakes are just really very chaotic systems that don't follow like a clear pattern. And so you not talk about main shocks or aftershocks, but rather, or swarms, but rather about an earthquake sequence. Another key component of this Argalojori earthquake was that on the one hand, it was very shallow. On the other hand, it was on the island of Crete, where usually the earthquakes happen in the sea around Crete. And then one thing that was reported several times is that it had like this very large acceleration of 0.8 G. So I think we probably first need to explain what one means by an acceleration measured in G,
yeah,
and why this acceleration was so high and so destructive for most houses in Argalojori.
Yeah, actually the magnitude is a number that is somehow related to the energy released by the earthquake. But what is more interesting for the people is the kind of ground shaking that they felt under their house or under their feet. So they are two different things, in the sense that, for instance, a magnitude 9 that occurs a couple of hundred kilometers on the sea maybe is not so dangerous like a magnitude 7 or a magnitude 6 that occur just in the middle of a city. For instance, I remember in Kobe in 1995 in Japan, there was a magnitude 7.1 inside the city of Kobe and caused thousands of people killed by that earthquake. So I'm saying that an earthquake, if it is close to a city and is more superficial, it could be much more dangerous than a larger earthquake that occurred a couple of hundred kilometers away. So, and we measure the kind of acceleration as a fraction of g, that is a gravity acceleration. So for instance, 0.1 g, it means 1/10 of the gravity acceleration. That is 9.8 meter.
So the gravity acceleration of the Earth.
Exactly. So it's just a useful metrics for us to say. So 0.8, it means that you are close to an acceleration that is close to the gravity acceleration of the Earth.
And so this is, by comparison, this is like a very huge or large number, right? 0.8.
No, 0.8 is pretty large.
So usually, this would be, sorry, this would be rather unusual for an earthquake in general, or like?
It's not unusual. Again, it can happen if the earthquake is very close to the building. And we know that this kind of acceleration tend to decay very rapidly in space.
So it's like with increasing distance from the epicenter, the acceleration decreases rapidly.
For instance, I see very strong acceleration also caused by magnitude 4 that were very superficial and very close to the buildings. For instance, there is some earthquake of magnitude 4 that caused casualties in Italy, in Casamicciola, that is in Ischia Island, because we know that the source is very superficial and very close to the buildings. It means that the seismic waves do not have any attenuation before reaching the point, before reaching the building. So again, the problem is complicated.
In simple words, what is attenuation for?
It depends on attenuation, of course.
Yeah, no, just the term attenuation, maybe.
Attenuation means that the seismic waves, every time that you have an earthquake, you create seismic waves, and the seismic waves can be, the amplitude of these seismic waves can to diminish with space caused by geometrical spreading, and also by the fact that the ground tend to act like a sort of filter in a way that they can tend to lower the seismic waves with space. There are rather complicated process, but in general, again, it is like the water wave. When you throw a stone into the water, you see that the biggest wave are very close to where the stone hit the water. And then there is some sort of geometrical spreading that tend to lower the waves, and then also some sort of attenuation with the distance that allow the waves to become nil when you arrive at a certain point.
Hardly observable.
Yeah.
You've almost answered like the next question I had about this other earthquake that took place, that was also magnitude 6 earthquake that happened about 2 to 3 weeks after the Attenuation earthquake, but in the sea on the southeastern part, in the southeast of the southeastern part of Crete. So there we observed like a completely different aftershock pattern compared to that of Arcalojori, which is kind of seems like a normal aftershock pattern. So there was this major quake and then a couple of aftershocks of magnitude 4, and that was it. So I know that there exist explicit models for modeling aftershocks, but here again, those models don't really seem to fit. So would you just again say that this is due to the chaotic nature of earthquakes and that every sequence is somehow different?
Well, I have to say that I don't know exactly, but the problem is that the model could use the same model for both earthquake. The most important point is that the parameters are sequence specific. So I'm saying that if you collect the few hours just after the big event, if you collect the few hours after the big event to calibrate the model, you can get a reasonably good fit of what happened next. I would say for both earthquakes. That's, again, is not surprising. I remember also in Idaho recently in the United States, a magnitude 6.5 that have a very, very low seismic activity after that. It is not surprising. It happens. It happens. We do not yet know why. The only thing that we know is that every earthquake participates to trigger other earthquake. So it means that if a large earthquake produces some earthquakes that are still large, they can contribute to give fuel to the sequence and allow the sequence to become longer. So again, we still don't know exactly. Sometimes we see, for instance, in exactly the same place or very close in Japan, I remember, two earthquakes of the same magnitude happen a few tens kilometers one from each other, 2 years of difference, they have a completely different aftershock sequence. We know that the kind of decay is sequence specific. Is not, you can use the same parameters for any kind of sequence. This does not work for sure.
Yeah, that kind of makes sense. So this takes me to the next question. So another key question, of course, was whether those two earthquakes in Nargalojori and southeastern Crete were somehow connected with each other, right? So there's this kind of domino theory, and if you think about it just intuitively without really having studied seismology, you would think that maybe the kind of some sort of slip or event over here then triggered the event over there. Like the distance, I looked it up on Google Maps, is between 90 and 95 kilometers between the two epicenters. So is this something that you would say, well, I don't know, or maybe, well, I'm pretty sure that they are connected, or are they not connected? What is your opinion?
I'm in the answer, I don't know, in the sense that we know that the earthquake tend to cluster in space and time. But usually for that kind of earthquake, 90 kilometers is a little bit too much. Again, I'm saying a little bit. I'm not saying that it's completely disconnected. I'm not saying that. One of the problems that, for instance, in time, we know that the seismic sequence can have an effect for a few years after the large earthquake. Of course, the effect tends to decay with time, but we see this recognizable increase of seismicity for a few years just after a main shock. But with for what concerns the distance is a little bit more debatable. Of course, I can tell you an earthquake that occurred 1,000 kilometers away, I say, okay, that's completely unrelated. But if you are, say, 90, 100 kilometers, I can't be so sure. And I would say nobody can be so sure. But sometimes we see that. I remember an earthquake in Mexico, a couple of earthquakes in Mexico that occurred very recently. One earthquake close to Acapulco and another earthquake inside inland. Both earthquakes were above magnitude 7, and they were very close in time, suggesting some sort of connection, but the distance was a little bit too much also for magnitude 7. Again, nobody can tell that. The feeling is that the connection, that could be a connection. Usually this kind of connection is very small in the sense that it happens very rarely, but it may happen.
And so if it happens rarely, we don't know if it just happens by chance or by some connection, right?
Well,
so
we don't know exactly what is the real distance from which there is a connection and there is no connection. Very likely the connection exists, but is still probabilistic, in the sense that when you are very close, this probability is very high to be connected. And this probability tend to decay with space. And let us assume that 100 kilometers, I have a connection that is 5%. it means that I could see this kind of situation 1 out of 20 times. So every time that you see is probably a surprise, but maybe it could be explained. Again, this is something that is still under study, but I think that nobody can tell you for sure that they are connected or they are not.
Yeah, I mean, I would guess a problem of your field of research also is that you don't have that much historical data, right? So you only have data for, I don't know when seismographs were introduced, but then like if you want to go further back in time, you have paleoseismology, which of course, which is very imprecise, you miss all the smaller shocks, etc. So is this a general problem of your field that you don't have that much, that you cannot go that far back in the past?
In particular, if you look at only one specific region, of course, we are trying to learn, looking at trading space, time with space, in the sense that we are trying to get some new insights, looking at sequences occurring everywhere in the world, under the assumption that the earthquake generation process is the same. And what we see is a different realization. Of course, there are peculiarities, of course. For instance, in Crete, there is a subduction zone. I can make a comparison with other subduction zone, not with a completely different tectonic environment. But you are right, in the sense that it is very unusual to find in a place like central part of Italy that is one of the best known historically, but in every single region, for instance, in California, it is very difficult to go much far back in time, in the sense that you don't see what happened 200 years ago or 300 years ago. That is the time scale for the earthquakes. And so what we try to learn is from different situations. For this reason, it's very important also to study the earthquake globally. In Crete, you have a very important history, but of course, it is not easy to have a complete catalog, seismic catalog historically. We know in Italy that there is a lot of problem to have this. And this is a limitation. Again, we are trying to learn something from similar sequences in different parts of the world that have similar tectonic environment.
I see. So let's get maybe back to Crete and the Hellenic arc again, because like, you know, with it, so there was a rather large period or long period of seismic peace, at least around Crete in the recent years. And so there has been some talk again on the media and the social media about like a more general activation of the Hellenic arc and increased seismic activity. And of course, there are those two recorded huge earthquakes in the subduction zone that you mentioned that were apparently magnitude 8 earthquakes, I think like 1,700 years ago and 2,500 years ago, if I remember it correctly. So what is your opinion about this?
Well, actually, that subduction zone can produce such a big earthquake. And probably there were such a big earthquake in that Hellenic arc. So this is a typical, the size of the arc can produce very large earthquake. We know that. As regards the quiescence that we have seen recently, that's normal. When the earthquakes are rare, even under the assumption that occur completely independently, you always find some period of time in which nothing happened. Again, the problem that we have is that the time scale of the earthquake is different from the human's time scale. So people just remember what happened the last decades, and they think that this is the normality. It's not. It's not the normality. And every time that we see something, we say, oh, this is a black swan. It's not a black swan. It's something that we know that could happen. We don't know exactly predict when, but we can say, yes, in the future, hopefully very far in time, there could be a very large earthquake in the subduction zone in that area.
Regarding like an activation of the more broad activation of the Hellenic arc right now, is this something you would want or even dare to make an assessment about, or would you rather say, well, you know, our understanding is so limited that I'm not in a situation, or my knowledge is not sufficient to make a statement about this?
No, actually, we are ignorant about that. We have to be very clear. The only thing that we know is that every time that you have an earthquake, is more likely to have other earthquakes. So every time that you see an overall increase of seismicity, there is also an overall increase of probability to have a large earthquake. But again, that the probability remains very low, as 1%. It means that most of the time nothing happened. This is not to reassure people or to scare people. That's what the natures tell us. Every time that you have an increase in seismicity, you might say, okay, the probability to have large earthquake is somehow increased. But let me make this point very clear. We are not absolutely in the position to make any prediction. We can make some sort of probabilistic calculation, but for magnitude 8, I can tell you that probability would be much less than 1%. That's just for my experience. Taking into account.
Going back to your statement that, you know, if you have some earthquakes, the probability that a larger earthquake happens or that there is increased seismic activity shortly afterwards increases, but still remains very low. So how does this higher but still low probability, how does this decrease with time if nothing big happens after like a series of big earthquakes?
More than nothing big, I say when this probability return to the background probability. Again, the decay is very quick, but we can see some sort of signal that can last for a few years. And again, of course, as long as you are far in time, that probability tend to return to normality. It's like, for instance, I see some the possibility to have a second metastasis from a cancer. Every time that you, with a surgery, you remove all metastases. For instance, for some kind of cancer, you have 5 years of period in which, after which you are safe, or at least the probability to get it come back to the normality. And that probability to get a second metastasis or something like that tend to decay with time. So again, is the most worrisome period is the first few months, first year. But again, you are not safe until the 5 years. And for the earthquake, I would say that is somehow similar in the sense that the biggest danger is nearby, few days, few weeks, few months. Then as long as the time goes on, everything tends to become to normality. But become to normality doesn't mean that the magnitude 8 cannot come out from the blue. Yeah, it can. That's something that we have to learn to live with that. And to me, that's very important to make clear this point, because sometimes the people tend to say, well, we are not able to predict earthquake. What are you talking about? Actually, I don't like too much the way in which seismologists have shaped this kind of discussion, because it seems that you are able to predict exactly an earthquake, otherwise you know nothing. That's completely wrong. We know something, and we try to express our knowledge in probabilistic terms. Probabilistic terms is like, again, you can see a very strong increase, but the probability remains low. Whatever low probability means, because the effect can be very important. That's somehow related to what we are living now with the pandemic. You say, okay, I don't care about getting COVID-19 because the probability to get a serious disease is very small. Other people are terrified with the same numbers. When you are talking about low probability, high impact event, the perception, personal perception play a major role. Some people is terrified, some other people simply don't care. And the numbers are exactly the same for everybody. And for the earthquake is the same. You increase the probability, you have 1% or less, but the probability of something very big, something very impact that can have a big impact. How the people react to this kind of information, you could have a completely divergent.
That's for sure. So before we go a little bit more into earthquake forecasting and prediction, like one more practical question to you, although I know that you're not really, doing civil protection, but research. But according to your personal opinion, not your opinion as a scientist, but your personal opinion, what are the best protective measures against earthquakes? So what can people do?
Well, the risk reduction is hardly a zero-sum game, in the sense that you might do something, you can do different things. And the first one is to be sure on the vulnerability of your buildings. This is definitely, when you know that your building is well built, you can live a little bit more easy, in the sense that you know that your building is well built. Again, it doesn't mean that the building will not be destroyed. It means that it is much less likely that the building can suffer some important damages. And most of the people have been killed simply because of the poor constructions. And this caused most of the problem. So building is a big issue, and it's definitely the most important point. In the short term, for instance, every time that you have an increase in probability to have a large earthquake, you can also take additional measure. Additional measure is, for instance, you can minimize your stay in vulnerable building. It could be like a church, it could be like maybe your house is very well built, but not the place where you work. There are some, again, you can stay more time out from buildings as much as you can, is a way also to minimize that. And of course, if you have the possibility, you can also visit your brother that live in a safer part of the country. Again, that's very personal. There is no, because most of the time, for instance, I remember once a very nice thing that has been made in Italy. There was a sequence in the Northern Apennine that lasts for a few months. And the mayor of this small municipality decided to install a tent camp. And they say, for the people that do not feel safe in their houses, they can go to sleep under the tent. That is much safer. And so the people did it. Some people did it, some others don't. Nothing happened, but the people were really happy to have an opportunity, an additional opportunity. And yeah, but the seismic sequences also is a teachable moment. So they can push the people to think about how strong is your building, how safe is your building. Otherwise, in normal period, it's very difficult to capture the attention of the people to check the vulnerability of their building. During the seismic sequence, maybe their ears are more open, and so they can maybe think about double checking the vulnerability of their house. That's definitely a very, very important point.
So this takes me like connected question to this is that in Greece, as far as I know, there are like 3 major seismic zones that kind of inform the respective building codes. So Crete is zone 2, and then the Ionian Islands on the Western Greek coast are zone 3. They have like the highest anti-seismic rules and the like, let's say the toughest or safest buildings. But then I read that, this 0.8 G acceleration that we had in Atkalahori was well above the maximum acceleration that was assumed for zone 3, so for the Ionian Islands. So how, how accurate do you think those zones really are? Do you think that there must be a process of constant readaptation of this classification? I would assume that you have something very similar in Italy.
Well, that's a very important point. Of course, I don't go too much into the detail because I'm a seismologist. I'm responsible for estimating at best the probability of ground shaking. But that is an important thing. We never can give you the maximum ground shaking that you can expect. We can't simply do that. If you want to do that, you can take 2G and you can build all the buildings for 2G. The problem is that this is not feasible, or is very costly to retrofit all the existing building to that. And that's probably not feasible. Again, this is not my job, it's the job of engineering community. Engineering community do not take the maximum ground shaking expected, but they take a ground shaking that has 10% of probability to be exceeded. And of course, this kind of modeling has to be updated regularly in time. But the most important point is that every time that you have a big earthquake, it's very likely to see some acceleration that go above the probability, the ground shaking that has been taken by for seismic building code. But also it's very important that this is not necessarily a big problem, because the buildings are built not to collapse on your head. So they can be completely destroyed, but you are safe. You can get out, the building is completely useless, then you have to rebuild from scratch, but you are safe. So there is some sort of additional safety measure that the engineering community usually takes. I don't know in Greece, because I don't know exactly the situation in Greece, but almost in every part of the world, they take a number. It doesn't mean that if you overcome this ground shaking, the house is going to collapse. No, it's not. But on the other hand, again, that's an important issue. The ground shaking that you usually see on the map are never the maximum, are never. Usually, they have 10% of probability to be overcome. Why 10%? This is not a choice of seismologists. They can take also the 2%. That means 2% higher safety, but it could be very costly, and somebody has to pay for that. So again, you understand that there is a very delicate balance.
Typical engineering trade-off.
Yeah, but it's not only engineering.
Right?
In Italy, we have the same problem with the pandemic. Everybody wants to lock down because we want to save all the lives. On the other hand, you say, okay, but if you lock down forever, our economy is going to collapse. And if our economy is going to collapse in the future, we will have less money to spend for healthcare system. That means that more people in the future will die simply because they can't be cured as we do now. Again, what is the right balance? I don't know. Frankly, it's not my job, but I see that this is a major problem, that usually people tend to make too easy. Say, okay, give me the maximum, and then I'm safe. That's not possible.
No, that makes a lot of sense to me. But you do, like in principle, you do agree that the building codes, the adaptation of building codes must be something like a permanent, perpetual process, essentially. That's where you readapt all the time the building codes and refine them, etc. So it's not something that we fix, but that is progressive, right? So this is something you'd agree to.
Yeah, maybe. Again,
okay, so now.
No, go ahead.
No, please go ahead.
No. I simply, I can't tell you too much because I'm very strongly respect the competences. And I'm not an engineer, and I know that the engineers have a lot of headache to handle the problem, because every time that you change the building code, somebody that has spent money to adapt their houses to the old building code, they say, oh, well, now I have to reinforce more, or maybe now the seismic hazard is lower. It means that I spent money that I could save before. So it is a very tough issue, and fortunately, from our side, we are just focused on trying to estimate what the nature could do, not how human beings will use this kind of information. That is pretty challenging anyway.
Okay, so now let's move on to tsunamis, which are of course also connected to the Hellenic arc. So first question here, they're also of course of concern to you because Italy is not that far away from the Hellenic arc. First, like an initial question is like after this earthquake in the sea southeast of Crete, there was like a tsunami warning issued. And the tsunami was measurable, but essentially not observable by humans. So what I heard or what I read are claims that, only for earthquakes with a magnitude exceeding 7 and above, so exceeding 7 on the Richter scala and above, a tsunami warning should be issued to prevent perceived false alarms. So what is your opinion about this?
This is just the starting point. For now, this kind of rules has been established in the whole world. So it's not only something that has been made in Greece or in Italy, in Mediterranean Sea. These kind of rules are the same everywhere. To me, there is room for improvement because, of course, the magnitude is important because we see very, very few tsunami caused by smaller earthquakes. But the situation, again, there is still some uncertainty because, of course, an earthquake can create a submarine landslide that can amplify the tsunami. And again, is something very tough. For now, in Italy, we have a very, very strong team working on tsunami, and they are very aware about the limitation, but they are made a very excellent job. But again, for now, just to keep everything comparable to what other people is doing, they have to follow the same rules. And magnitude 7 is a threshold to raise an alert. Also take into account that another very important problem that is not related to us, but is related to the society, is what is the level of false alarm or the false alarm rate that can be tolerated by society. For instance, what I'm saying is that if you raise an alert every day, at a certain point, people simply don't care, simply don't listen to you anymore. But on the other hand, if you just try to reduce too much, you can be hit by tsunami without an alert. Again, as before, there is a very delicate balance, but from a touristic point of view, most of the time it's not a big issue. You are on the beach, you simply have to walk or take a car and going far from the beach or higher level. If there is a mountain, you can go there, like usually people do in Hawaii, for instance. And in this way, you can be safe with a very, it is not very expensive for you. It's not very expensive for you. As a tourist, of course, if you are an industrial activity, I don't know exactly what the problem could be for a tsunami alert. Again, every single stakeholder of this kind of information could have completely different tolerance to the false alarm rate. And this is also something very important to take in mind. As a tourist, I can tolerate, okay, I stay here a couple of weeks, so if I have one alert, who cares? But for the people living there, for the people working there, the too high alarm rate could be very, very disruptive. So again, the right balance is not the work in the hand of seismologists, of people working on tsunami, but is the people that has to make decision for society, has to make decision for critical infrastructure. I know that this is tough. Usually people tend to think too simply to this problem. I think that is very important to think that this is a very, very tough problem. And the risk cannot be set to zero, almost never. And at a certain point, you have to define what is acceptable risk for you. And again, this is something that is not made by seismologists or by people working on tsunami.
But I believe it's also a matter of information and education, right? Because I mean, you really need to know or have seen somewhere how the sea behaves when a tsunami comes, and be able to identify it. So, and given that tsunamis travel that fast, like on average, I think 800 or 900 kilometers per hour, if something happens at the Hellenic arc, you know, it will be just a few minutes until it arrives on the beaches of Sicily. So, you know, one part is education, but I mean, you know, maybe we would need some sort of early warning system or a Mediterranean tsunami center or something like this. Is this something that exists, or are there thoughts about establishing something like this for the entire Mediterranean?
I think that in Italy is something that is undergoing. But if a magnitude 8 occurs in the Hellenic arc, I think that you don't need, for instance, sirens to tell you to evacuate the beaches, because you feel a very strong shaking. Every time that you feel a very strong shaking on the beach, go away, go away. And this is also for Sicily. In Sicily, a magnitude 8 could be felt very clearly. So for this reason, it's more important in the beaches that do not feel the earthquake. Like for instance, in Thailand, when it happened, the earthquake in Indonesia, all the people were not aware about the earthquake. And so they simply don't know exactly what happened. And again, if you see some sort of very strange behavior of the sea, this is very dangerous sign, so go away. Of course, there could be some sort of sirens, or I don't know, maybe something on the mobile to tell you something. But you correctly say, if I'm close to the earthquake, it's a matter of time to be alerted. But on the other hand, you feel very clearly the earthquake. So if you are on the beach, okay, talking as a citizen, not as a seismologist, if I'm on the beach and I feel a very strong earthquake, I just simply move away from the beach. Maybe there will be no earthquake, no tsunami.
Every generation needs to. Yeah, but every generation needs to learn that and needs to know about this. I think that's also one of the main issues. So now I'm really sorry about this question, because you've been asked the same question like a million times before, I'm sure. So can we actually predict earthquakes?
Well, I don't know. Maybe predicting the evolution of science is more difficult than predicting earthquakes. So I don't know if in the future we will be in that position. I can tell you now we are not. At least we are not able to predict earthquake as the people would like, in the sense the day, the place, and the magnitude of a big earthquake. So we are not in that position. Again, this does not mean that we know nothing. We know that, for instance, during a seismic sequence, the probability to have large earthquake increase significantly, but that probability per week usually remain below 1%, let's say, below a few percent for sure. This is what we know. And I understand that I'm very happy to be here with you, because I'm a seismologist, I'm not a communicator, I'm not an expert in communication, but I think that we have to make a major effort, try to communicate with society. And I don't know if I'm the right person, because this is not my job to communicate, but I think that is important at least to try to convey to the people what we know. And every time that you heard there will be an earthquake, this is a fake news, for sure, for what we know now. In the future, I don't know, but for now, that's impossible. But again, during a seismic sequence, be aware that the situation is not like when you don't have a sequence. It's
right.
more.
So the probabilities change, but they nonetheless remain probabilities. So
Absolutely,
it's not
absolutely.
kind of prediction. So
that's also
when we last.
That's a very important point, because the people, actually, from what we know now, the probability is the language of nature. I know that the people do not like probability, but this is not something important. The nature keep going in the same way. If this is a language of nature, we have to learn how to handle with this kind of information. And again, I understand that people want to say, for sure, it happens, for sure it doesn't. We are not in that position. Probably we will never in that position. But this is for the earthquake, but this, I could say the same for many kinds of natural risk, also for pandemics. The problem is that if this is the language of nature, we have to be educated since the beginning, since when we are kids, about the language of probability. And this is, to me, the biggest gap that we have in trying to communicate with society. That I see with the pandemic again, I see a lot of probabilistic information given to the layman that are completely misleading, and people do not understand them. And this is a problem. This is a real big problem that we have.
Yeah, I understand you. We actually did like a fun little work on predicting the European Nations Football Championship, like a tournament prediction, which is very difficult, especially in football. And then we ended up with a winning probability of 15% for France, and then France didn't make the final, and our prediction was totally wrong. So this is, I think this is really a very big issue in communication and education, that we need to think more in probabilistic and stochastic terms. Another question that is related to earthquake prediction, and when we talked last time, you mentioned that you're making the distinction between prediction and forecasting.
Yeah.
So which for most people, you know, those two words are essentially synonyms. So could you maybe explain to me how, you know, what prediction is, at least in seismology, and what you understand as forecasting in seismology?
Yeah. The prediction is a deterministic statement. This is going to happen or not. It's a deterministic statement. And again, we do not have any knowledge to do this in a rational way. The forecast is a probabilistic statement. We can always release a forecast, always, depending on the kind of knowledge, the kind of data, kind of information, we can always release a probabilistic forecast. That again is a probability. It can be understood what it means. It is not certainly any kind of prediction. And for this reason, we like to make this distinction. In Italy, we have only one word, previsione. And in English, at least we have two terms that can be used to make this clear distinction. We are not able to predict earthquake, but we are able to forecast earthquake, almost always. Maybe the forecast could be good or could be bad, I don't know, but we can always make a forecast. Or sorry, I used the wrong word. It could be based on a lot of data, or it could be based on a few data. But we can always make a forecast about something.
So if you say that we cannot predict earthquakes, but we can forecast earthquakes. So how would you kind of measure the accuracy of the earthquake forecast? So how would you say that, you know, this is like a good forecast or a bad forecast, or my forecast is correct like in 10% of the cases? So how do you assess the accuracy of the earthquake forecasts?
Now, this is a very good question, because testing a probabilistic forecast is far to be trivial. And what we do usually, we usually have a collaboration, a collaborative, the CSEP activities is the collaborative studies for earthquake predictability. that is focused on testing the earthquake forecasting model. What we can do it is just to see if 10% on average means that 10% of the time something is going to happen. Of course, this can be made averaging over a large area because you can't test a model in every single square meter of the whole country because you do not have enough time to do that. But this is something similar to what people in the weather forecasting community is doing, in particular for testing some extreme situations like a very strong excess of raining or wind. We have similar problem. Of course, if I can easily test my model, if I'm interested in testing if my model is able to do a good forecast about the magnitude 3 or magnitude 2 that are small earthquakes that occur more frequently. This is exactly the same for weather forecasting community, in which they can test the model for regular amount of rain. When you want to test the right tail of the distribution, in other words, when you want to take extreme event like big earthquake or big extreme event, it is much more complicated. We usually trade space with time to make some sort of preliminary test. We do a lot of work, and this work is strongly in progress. But yeah, that's something that we do. But of course, there is a lack of data, in the sense that we can say, okay, with the data that we have available, this model seems to work well. This is what we can tell.
Yeah, because you're just lacking the historical record in a certain sense. So another question that is kind of related to forecasting is to which extent you believe that modern machine learning methods, artificial intelligence methods, will help us to at least, if not to predict, but at least to improve the forecasts.
This is a new field of research in seismology. The problem that I see is the same problem that I see for testing. We have very few cases with a good amount of data that happened before large earthquake. So we have plenty of cases in which nothing happened. We have a very few cases in which a big earthquake happened. And so try to learn from a limited amount of data could be a limitation also for machine learning techniques or something like that. So yeah, the biggest limitation is the amount of data that we have before large earthquake, basically. So it is the same problem that we have for testing. But I see a lot of attempt made by several groups worldwide to try to apply these new techniques to try to see if we can see something that is not visible with the classical kind of analysis that we do.
I see. So so this is kind of maybe related to gathering data and integrating data from all over the world. I don't know, but like, what do you think needs to be done at a national level? For instance, in Greece, I don't know how well you know the community here, in Italy, and also at an international level, to improve earthquake prediction and forecasting and general kind of foster earthquake research?
I think that to me, we have to start from the data, collecting the data at the best that we can. For instance, now there are a new high resolution catalog in which you have a catalog. The high resolution catalog.
So a catalog, sorry, for the general audience, like a catalog, what is this? Just
sorry,
like a
earthquake.
list of coordinates and magnitudes and like basically a list of earthquake data.
Yeah, the earthquake catalog is a collection of information about the time, location, and magnitude and depth of an earthquake. We have regular earthquake and we have higher resolution catalogs that are made with many machine learning techniques. In this case, the new high resolution catalog can be 10 times larger, even more with respect to the classical catalog. Of course, most of the earthquakes that are added are small earthquakes. But we think that we can still learn from small earthquake about what may happen for the largest one. And this is something that to me is very promising. Again, as I told you before, I can't predict the evolution of science, but one thing that is important to me is to improve significantly the quality of our catalogs, instrumental catalogs, and also, if possible, also to gather other kind of new information, like information coming from satellite. Again, this kind of information could be very important. The limitation is that we have this kind of information only recently. But maybe, as long as we go ahead, maybe we can find some sort of pattern into the deformation before large earthquake. I don't know. But it's something. The feeling is that with the amount of data that we have almost explored everything that we can do. We need more data, definitely.
Like in a way, it would be cool to be able to time travel like 1,000 years ahead and be a seismologist like in the year 3021 or something, right?
Yeah, absolutely. So the problem is that we have to start. And again, there is a lot of attempt to do that. For instance, in central part of Italy, for the sequence central part of Italy now, the new high resolution catalog built with machine learning has more than 2 million of earthquake for that sequence. So it means that we can see a detail about how the seismic sequences evolved through time and space that we never had in the past. I don't know if this is important or not. But of course, we know that with the amount of data that we have right now, we have almost done everything that we can do. This is the feeling. And we need more data from earthquake. We need more data also coming from other kind of observation that we do not consider now. Yeah, but
typical
maybe
data integration, heterogeneous data integration kind of challenge that we're facing in many domains of research, essentially.
Yeah.
So one very last question. So somewhere I read that it's better to invest money in earthquake prevention, like buildings, training, etc., than in earthquake prediction research. So what do you think about this statement?
Well, again, it's not a choice. To me, it is true that we have to spend money for prevention. That's definitely true. But this does not mean that you have to only do this, because every time that you can add some additional information, of course, this can be very helpful also for taking other kind of mitigation action. Let me make the case. If you spend money to increase the capability to collect data, this could be also helpful in the long term to have a much better view about how the seismicity behaves in the long term and then to build better. On the other hand, having more data, you could find something also for the short-term forecast. That could be very helpful, fine. Again, I don't see that is wise to spend all money in one direction. But again, it depends on how much money you have. If you have a very few amount of money, I understand that. And for sure, building better is very, very important. Is our first defense. But again, it cannot be made always. And on the other hand, if I know during a seismic sequence, I know that the risk is increased, I would like to have this information. I would like to have, because now I can't do anything more for my building, but I can decide to spend some time outside the houses. So it depends how much money you have. You have in our report as International Commission of Earthquake Forecasting, we explicitly said that money has to spend in a balanced way. Of course, the long term, the building well is very important. On the other hand, spending some money to improve the data that we can collect can give you a lot of insights, not only for the predictions or for forecast, short-term forecast, but also for the long term. So we have to spend some money for improving our research capability.
Yeah, so there must be some money invested into, you know, high risk, potentially high risk, but also potentially high gain research, right? Because
absolutely,
that's how we may eventually one day. I mean, I cannot predict the evolution of scientific research either, but maybe one day we might be able to predict earthquakes.
Yeah, but please take into consideration, even if we are able to predict perfectly earthquake, if the buildings are very poorly built, you can save your life, but when you come back, you see a city completely destroyed. So again, it's challenging. Again, you have to look at the problem from a wide range of perspectives.
I think this is a very good closing phrase for our interview. Warner, I thank you so much for taking the time to giving this interview today, and I hope that it will also be of interest to the broader public in Greece and Italy, and maybe around the world, hopefully.